Hello everyone. In this recording, we try to convert this pseudocode, which is a greedy algorithm for a knapsack problem based on the ratio criteria, to a Python code. And from now on, we do not use the AI assistant to do this conversion, and we try to write the code from the scratch by ourselves. So looking at this pseudocode in the first two lines, we need to first define our inputs and also our output variables. So we are going to use this parameters, these values that we have for this instance, and we start converting them, writing them in Colab. In this file, which is the knapsack greedy, we are going to write those input parameters. So the ground set is the set of all the items that we have in this problem, and the W is the list of the weight, which is these values, and also we have the small v, which is the list of values, which is 6, 8, 9, and 10. And finally we have the capital C, which is the capacity of the knapsack, which is 7 in our problem. So let me add a comment here. So we have the inputs here, and also we need to have let's say the outputs. And for the outputs, we need, based on the pseudocode, we need two variables, the capital S, which is the set of selected items, and the f of s, which is the value of the corresponding objective function. So we define the capital S here as an empty list, because we know that we eventually need to add some items to that empty list. So at the beginning it's an empty list, and we define the small f as 0, which is the corresponding value to choose nothing from that ground set. So having those things, we can define them, and let's go to the next cell. And what we need to do here is to defining this remaining capacity variable, which at the beginning equals to the capital C, and also we need to define the capital F, which based on the definition here is the set of feasible candidates. All the items belongs to the ground set, which their weight is less than or equal to the remaining capacity. So let's go to Colab and define those two variables. So the first one is remaining cap, which is equal to the capital C at the beginning, and then we need to define the F. So to define the F at the beginning, so F is all the items, because at the beginning the remaining capacity is equal to 7, and we know that all of the items could be fit in an empty knapsack, so all of them belongs to that candidate set. So but how we are going to define it? We are going to define it as an empty list at the beginning, and then what we need to do, we need to follow this rule in these curly parentheses. So we need to check all the E, all the I, all the items belong to that ground set if their WI, if their weight is less than or equal to the remaining capacity. So we are going to convert this exactly to Python. How we are going to do that? So we need to go through all the items in the ground set. So we need a for loop. So we set for I in E, which is the ground set. We check all of them, and we then have that if statement that we are checking the W of that item. So if the W of that item, which in our case is I, but -1. Why this -1? Because we know that the indexing starts from 0. So if the W of I, the first item, -1, now we're looking for W0, which corresponds to the weight of the first item. So if Wi -1 is less than or equal to the remaining cap, remaining cap, then we add that item to the capital F list. So we have f dot append that item I. And then to see what is the output, we can have this print here, print f, and see what is the output. So as you can see at the beginning, the capital C is equal to 7, and all the weights are less than 7, so all of them could be added to that empty list. So the F, which is the set of feasible candidates at the beginning, is all the items, which is equal to the ground set that we have here, the capital E. Okay, so we have this F here, the capital F here, and then we have our loop here. While F is not empty, do something. So when we actually going to convert this one. Okay, let's before that. So we have this file. So we are looking for this feasible set of feasible candidates, and as long as we have some possible candidates, what we do is to using this criteria, which is the ratio criteria, the value of the item divided by its weight, and we choosing the item with the maximum ratio, so that we call that item as I star, and then we add that I star to the list of capital S, which is the list of selected items, and therefore we need to update the value of the objective function, which is simply adding the V of I star, which is the value of that selected item. We need to update the remaining capacity. So the remaining capacity is what we had so far, minus the W of I star, the selected item, the item that is now in the knapsack. And also we need to update the F, the set of feasible candidates, because now the remaining capacity is updated. Therefore we need to update also the capital F, which is the set of feasible candidates. So this is the thing. So we need to choose the best item, add it to the list, and then update the objective function, remaining capacity, and the set of feasible candidates. So let's go back to the Colab. So we have that while loop. So while f, which is the set of feasible candidates, so the len of f is not 0, which means we have something in f. So this is exactly what we had in the pseudocode. Len of f is not 0, which means there is some possible feasible candidate in set f. What we need to do is to look for the best ratio, the item with the best ratio. So if you remember from the previous recording how we update the value of the objective function, and how we update the value of the best solution and the best objective function, for example for the random search or for the exhaustive search, this is going to be exactly the same as what we did for those problems. So what we need to do is first to define uh, something like, let's say, the best I, and the best I is the first, let's say it is the first item of the feasible, the capital F. And also we have the best, let's say define it the best ratio, and the best ratio is the ratio of that item, the first item. This is something that we can also start from the last item. It doesn't matter. We just need an initial value for the best item and also for the best ratio. So for the best item, we choose the first item in capital F and set F, and we also choose, we need to calculate its best ratio, which is the V, the value of the best item minus 1. This minus 1 is again this because of the indexing, divided by its weight, which is the best I, again minus 1. So the initial value for the best item is the first one, and therefore we calculate the best ratio based on that item, which is the value divided by the weight. So when we have those things, we need to go for all the other items in the F and see if there is anything better than this item or not. So we need a for loop. So for j in F, what we need to do is to see, first calculate the ratio of j. So the ratio is the v of j minus 1 divided by the w, the value, divided by the weight of that item. So we have this ratio variable, and if this ratio variable is better than the best ratio, so we need to update that item and also the best ratio. So what we need to do is have an if statement. So if ratio is greater than the best ratio, which means we have a better item, so what we need to do is to update the best ratio, which now is going to be the ratio, and also we need to update the best I, which now is going to be this item j. Sorry. So here's the thing again, we use the first item to be the best item, and then we calculate its best ratio, and then we look for all the other items, remaining items in the set F, to see if we have something better than this item or not. If there is such an item, we need to update the best ratio and also the best I for that item. In this case, when we are done, when we are out of this for loop, which means we choose our best possible option among the candidate options or the candidate items, so we need to add this item to our solution list, which is the capital S here. So we need to s dot append best I. So now we add that item, selected item, to the list of selected items. And so we update the S, therefore we need to update the objective function. So the objective function, which was f previously, a small f, is going to be f plus the value of that item. So it's going to be the v of best item best I minus 1, again because of that indexing thing. So we updated the S, we update the objective function, and what we need to do right now, based on the pseudocode, we need to update the remaining capacity here. So we have this one, we added the I star, which is our best I, to S. We updated the objective function. Now we need to update the remaining capacity, and also we need to update the set of visible candidates. Going back to Colab, so the remaining capacity, which is the remaining cap, is the remaining capacity, but we had minus the W, the weight of that item, which is the best I minus 1. Okay, and here we have this one, and finally we need to update the F. So F, again, what we do for F is the same as here. How we generated the F, we are going to do the same thing, but this time we need one more condition. The only condition that here we had at the beginning was to make sure that the W is less than or equal to the remaining capacity. So it is possible, it is feasible to add that item to the list. Here we have one more condition, and the condition is that that item shouldn't be in the capital S, which is the list of selected items. So we actually need to get rid of that selected item and shouldn't have this in the capital F anymore. So again, we define F as an empty list, and we said for I in E, which is our ground set, if I not in S. So we don't want that item to be in S, so we are looking for the remaining items, the items that we haven't selected yet, and the W of that item, which is I minus 1, is less than or equal to the remaining capacity. If such thing exists, then we need to append that item to the F. Okay, and then we have our updated F here. So again, we started from an empty list. We check two conditions: if that item has not been selected yet, and its weight is less than this remaining capacity, which is the updated remaining capacity, considering all the items that we have had selected and added to the solution list, which is the capital S. And then when we are done, we have this update, and so we go for we do this until that F list, which is the list of feasible candidates, becomes empty, which means the length is going to be equal to 0. When we are out of this while loop, and what we need to do is to print out the solution of the problem. So we print S, and we also need to print the objective function, which is the F. So we can add some something here. We can say the set of selected items, and then make this one here, and here we can have let's say the value of the knapsack. So let's see what is our result. So if we run this code, we have some error, and this is not column. So the best I is this one, and oh yeah, this is the f of 0, so the best I is this one, whatever it is, minus I, and okay, so this is the, oh yeah, I made this mistake. So here's the thing, sorry. So we need this one, yeah. So now let's run it. So the set of selected items is 1 and 2, so we choose, it said that it's better to choose the first and the second item, and the value of the knapsack equals 14. So if we go back, we choose these two items, which their weight, the summation of their weight is equal to 5, which it's a feasible solution, and the summation of their value is 6 plus 8, which is 14, which the same as what we have here. So again, one thing that you need to to have in your mind is that this solution, there is no guarantee that this solution is the best solution, but this is the fastest way to have a solution, a feasible solution for your problem when the problems are become larger and larger. Okay, so with this I conclude this recording and hope you enjoy that.